might have heard that the sun, like many other stars, is made up of hydrogen and helium. So how did we know that? How do we know the composition of the sun or any of the stars? So we know that by analyzing the light which is coming from the sun. So how do we analyze the light coming from the light source? How do we get the spectrum of the source? So to know more about that, let's go to the optics lab in the dark room. So while you're doing the experiment, the room is supposed to be dark like this, but for the purposes of this video, let's switch on the lights. So in this experiment, what we are going to do is to analyze the spectrum of light coming from this mercury vapor lamp. So as you can see, the light appears white, and obviously it's made up of a mixture of colors. So our aim is to split the white light into its constituent colors. So for that, I have a grating placed over here on this grating table. Now the grating may look like a plain piece of glass, but actually it's made up of a large number of splits which are very closely spaced. In fact, there will be thousands of slits in every centimeter of this. And this grating will produce the spectrum, and to analyze the spectrum, I have the spectrometer over here. So let's look at the different parts of this spectrometer. The spectrometer has a collimator. So the function of the collimator is to produce a parallel beam of light. This parallel beam is going to be incident on the grating. Now the reason we want a parallel beam is that we want to satisfy the conditions for Fraunhofer diffraction. In Fraunhofer diffraction, a parallel or a plane wavefront is incident on the grating, and then we look at interference of plane waves which come out of the grating. That's why you have a collimator. So the collimator is essentially having a slit. So a very narrow slit is over here, and you can adjust the spacing of the slit, make it very narrow. Then what you do is, by adjusting this knob over here, you can make sure that you get a parallel beam out. That is, the slit should be, by adjusting this, you are making sure that the slit is at the focus of the lens which is in the collimator. So once you have a parallel beam of light coming from the collimator, that should be incident normally on this grating. So by rotating the grating table, you can make sure that the light is incident normally. Then what you do is, you look at the interference pattern on the other side using this telescope. So the first thing you have to do is to focus on a distant object and make sure that you get a sharp image of the distant object. That means you are focusing the telescope at infinity. So once you have focused it, you can look through the telescope, and this is nothing but the direct beam, and make sure that you get a fine, very well focused image of the slit. So this is known as central maximum. But then if you rotate this telescope like this, you will be able to see the other colors. In fact, you will be able to see the complete spectrum obtained from this grating. It will be difficult to see through this telescope, so we have the same spectrum over here. So you can see the entire spectrum starting from violet up to yellow. In fact, there are two very closely spaced yellow lines. So you know from the grating equation, d sin theta, z sin theta is equal to n lambda, that if lambda for a particular color is more, then the angle of diffraction is going to be more. That means you will get violet light which has a lesser wavelength towards the center, and the yellow line will be farther away from the center. So you will get in the first order spectrum all the colors from violet up to yellow. So what you have to do is rotate the telescope and make the cross square coincide with the yellow line, second yellow line, that is yellow 2. If required, adjust the focusing till you get a sharp image. Then note down the reading on any one of these two scales. So here you will have a main scale and a vernier scale. So the least count of the main scale is half a degree and the least count of the vernier scale is 1 minute. So note down the angular position of the cross wire on any one of these two scales, and stick to the same scale throughout the experiment. So these two scales simply differ by 180 degrees and there are two scales just for your convenience. So far I have been rotating this telescope by hand. In case you want to make very fine adjustments, what you can do is lock the position of this telescope using this screw. So now I can't rotate it by hand, but then I can rotate it using this other screw. So by turning this screw, you can rotate the telescope by very small amounts. So this will help you when you want to move from, let's say, yellow 2 to yellow 1. So what you have to do is measure the angular positions starting from yellow 2 up to violet on the left side, and then move to the right side. You will get the same colors in reverse order. That is, first you will get violet, and then you will get green, and then finally yellow. So throughout the experiments, while you are taking readings, you should move in only one direction. This is to avoid the backlash error. You should not move back and forth while taking readings, which will introduce an error in your experiment. So this is the basic principle of and working of the spectrometer, and then what you are doing here is essentially you are calibrating the grating. That is, using the equation d sin theta is equal to n lambda, and since you are looking at the first order spectrum, you take n is equal to 1, and you assume the values of the wavelength of the different colors which you are seeing, and using the grating equation you can plot a graph of sin theta versus lambda, and the slope of that would be 1 by 2. So you are finding out the grating constant in this experiment, or in other words, you are calibrating the grating. So that's all about the diffraction grating, where you want to obtain the spectrum of mercury vapor. Now we move on to the very next experiment, which is essentially same in most aspects, except that now we are going to look at light coming from the sodium vapor lamp. Now the sodium vapor lamp is supposed to have only yellow. You can see it's yellow in color. You might see a few other colors which are probably due to some impurities in the lamp or light coming from elsewhere. In fact, the sodium light from the sodium vapor lamp has two very closely spaced lines at wavelengths of 5890 and 5896 angstrom. So that they are separated by just 6 angstrom. So what happens is that in the first order spectrum, these two lines will be very closely spaced, and you will not be able to resolve them usually. Okay? So what you do is treat them as a single line in the first order spectrum. Again, take readings on the left side and right side. So if I take the difference between these two readings and then divide by 2, I get the angle between the center and the diffracted beam. I get the angle of diffraction which appears in the grating equation. So after taking the readings on the left and right side in the first order, what you should do is take similar readings in the second order. So I take readings for yellow 1 and yellow 2 on the left side, and then move and take same readings for yellow 1 and yellow 2 on the right side. So you have to do this very carefully, because the yellow 1 and yellow 2 lines are going to be very closely spaced. So what you can do is you lock this in position and use this small screw to make very fine adjustments. So while you are moving from yellow 2 to yellow 1 or yellow 1 to yellow 2, don't move the telescope by hand, because you can't make very fine adjustments. You will have to use the screw and make a fine adjustment. So I think you have a clear idea about how to do this experiment. I have not gone into the detail. Rest of the detail is same. When you have a collimator, you have the grating on this table, and then you have the telescope. The initial adjustments are exactly same as in the previous experiment.